These next videos go with section 3.4 in your text.
We're talking about transformations. It turns out that you can do several transformations, one after the other. And when you do that, you're actually getting a more complicated transformation. You put them together, these are actually called compositions of transformations. Let's take a look at some examples and see some really cool, surprising things when you compose different transformations together. Let's check out the first one. So we're given the triangle ABC, and we want to reflect it across the line L, and then translate it along the vector V. So here's what we've got. We've got this triangle ABC. Then we're given this line L. The first thing we want to do is take the image and reflect it over the line. We can sort of put it, I'll do it sort of informally, sort of put it like over here, like a mirror image. And then shift it by this vector, which means I take every point and move it that far over in a direction that's parallel to that. So it would look like that. In fact, that's actually the answer. Let me just make sure that we see how we got it. So we started over here. To reflect it, remember how you actually reflect over a line really fast. Let me just remind you. For every single point, what you've got to do is you've got to find a midpoint that's exactly opposite of that line. The way you do that is, for example, to find where A gets mapped to, the image of A, what you do is you would draw a line that's perpendicular to the line L that passes through A. So imagine a perpendicular line that goes right through it. And then measure that distance here and go that same distance here, and that tells you the reflection of A. Take the perpendicular line that's perpendicular to L that passes through C, and take the length from the line to C, and then go down that same amount. That's the image of C, and similarly for B. So when you actually do the mirror image, or the reflection, you get this. And it does sort of, isn't it sort of amazing how it looks like a mirror image? It looks like you have a mirror there and you're doing that. Now, to shift by a vector V, what you do is you take that vector, and you can't shrink it, you can't elongate it, and you can't twist it. So it's got to be parallel to that original vector there. But you just got to sort of put it at each of the ends, and you see where it points to. That's that point. It's sort of like that game. You have to put your feet on different colors and stuff, and your hands. There's that point. And, oh, wait, I'm trying. I'm really trying to do this live for you. Oh, I want to do it live. I want to do it. I want to do it. I can't do it. I can't. All right, hold on. Let me try one more time. Yeah, you think it's easy. Wait till you try your homework. All right. I'm just kidding. All right, here we go. And there you see it. So now you see those 3 points? Finger, finger, arrow? That's the shift. And if we do that for real, finger, finger, arrow, we get the answer. And so, how would I label this? Well, I'm not going to move it back. I've spent too much time. Remember, that point there goes to here. That's where the A point goes. And that got shifted to here. This is actually A prime. This B got way down here and got slid over, so this is B prime. Got to label it correctly. C goes to here, and that's C prime. And so, in fact, that is the image under this composition of transformations. Very cool. Let's take a look at another example together. They're sort of fun, you know? I have to admit they are sort of fun, even if they are a little frustrating. Can't draw them. All right, so here we go. Let's take a look at the coordinate plane. And I want to rotate this triangle JKL, 90 degrees counterclockwise about the origin. And then I want to reflect it over the x-axis. All right, so the first thing I want to do is want to rotate 90 degrees counterclockwise. And let me just remind you an easy way to do that. If you have a point x comma y, where would that point get mapped to? Well, that point would actually get mapped to negative y comma x. That's how you actually shift the entire coordinate plane 90 degrees counterclockwise. Okay, so in this context, let's see where in fact points would go. So let's take a look at J right here. So J, which is 3 comma 2, would go to negative 2 comma 3. So negative 2 comma 3. So I'm going to call this point here J prime. Now let me just warn you that things are going to get a little bit crazy. But that's J prime, negative 2 comma 3. Let's take a look at k, see where it gets mapped to, that's 0, 1, that would get mapped to negative 1, 0. So negative 1, 0, this point right here, I'm going to call that k prime. And finally, what about L? So we're going to shift that up 90 degrees counterclockwise, so it should probably be somewhere around here. 3 comma negative 2, 3 comma negative 2, negative negative 2, which is going to be 2 comma 3. So 2 comma 3 right here is L prime. So if we now connect those with straight lines, we're going to actually see the triangle. Now we're not done yet, because that's just the first transformation, the rotation. Don't forget, we want to then flip it over the x-axis, right? Or more fancily put, we want to reflect it over the x-axis, which means that we don't change the x's, but the y's become negative y's. So if I now want to reflect over the x-axis, what that does is it takes y's and sends them to negative y's, and the x's stay the same. But visually, it's clear, and I'm going to do it for you right now live, even though everything's going to get a little bit crazy. All I do is I just literally pick up this picture and flip it over. So you got to flip it. You got to flip it good. And that's what you look like. So this now becomes my J double prime, which you can see is negative 2 comma negative 3. Notice that this point is my K double prime, which is the same as K prime, because you see when I take that point on the x-axis and flip it over the x-axis, it doesn't change at all. So that's pretty cool. And you can see that this point right here is my L double prime, which you can see has coordinates 2 comma negative 3. Now, why am I using double prime? Well, because what I'm doing basically is I'm thinking about every time I have a particular transformation, I'll call it a prime. And so then I'm taking sort of like a prime of the other primes, so I'm calling them double primes. But anyway, that's what you can see what they look like. I should actually technically color that purple. I won't, but I'll do it here. See, now it's purple. So you can see that, in fact, there are two transformations that went on here, and when we put them together, we get this interesting composition of transformations. I want us to take a look at an application that's going to really lead to a very cool idea. Let's check it out. Tabitha is creating a design for an art project. She reflects a figure across line L, and then reflects the image across line M. Our mission is to describe a single transformation, just one transformation, that moves the figure from its starting position to its final position. So the point here is that if we have several transformations, sometimes we can actually describe it as one single transformation. Pretty cool idea. Let me show you two general illustrations of this so you get an idea of types of things that we can possibly see. Suppose that we have two lines that are parallel. So here are two lines that are parallel. And I reflect first around one line and then around the other line. Check it out. Here's a triangle. I reflect along this line. Bang, I get this dotted triangle. See how it's reflection? Now, forget about that line. Take a look at this line. And suppose I want to now take this dotted triangle and reflect it around here. Bang, I get this. That's straightforward. But now, start at the beginning and look at the end. How did I go from here to here? Notice it was just one transformation, right? It's a translation in this case. So this translation from here to here captured the spirit of a reflection and then another reflection over two parallel lines. So you have two parallel lines, you're doing two reflections. It's actually equivalent to just one translation. That's pretty cool. That's pretty cool. Let me show you another one. Sort of a generic one. So let's do the composition of two reflections across two lines that intersect. So they're not parallel, they intersect. So here's a line, here's a line. So let's check out the first line. Take a look at this line. Here's a triangle. Let's flip it. Oh, sorry, let's start here. So here's a triangle, here's a line. let's flip it over this line. There you go. So I reflect it over here and I see it's here. Great. Now forget about that line. Take a look at the dotted triangle and now reflect it over this line. Bang. So it's there. So what's the total result though? Well, notice that I went from here to here. It literally is just a rotation. And in fact, we can give the angle of rotation. You take a look at whatever this angle is and just double it. Because in some sense you're sort of doing it twice. You're sort of coming around once and then again. So you can actually figure out exactly what you've got going on here. If you do a reflection across two lines that intersect, you actually have a rotation. All right, so in this context, let's take a look at the Tabitha application once again. First, what she does is she takes this shape and she reflects it over the line L. So let's do that right now live. I'm going to reflect this over the line L so you know what to do. So sort of come down and reflect it. So it looks like a mirror image. I think it looks something like that. And then reflect over the line M. So now we got to reflect over the line M. So now I got to imagine this line is sort of picking up over here. So reflecting over here, like a mirror image here. Something like this maybe. Now what's the net result? Well, since I'm doing reflections over two lines that actually intersect, I know really it's just a rotation. Rotation of what? Well, I see this is 60 degrees. I double it and see 120, and that's the answer. This is a rotation of 120 degrees about the point of intersection of line L and M. Let me just sort of show this to you visually really fast. If I start here, if I just now twist it over, rotate it about this point, 120 degrees, you see I get exactly that thing. Same thing as reflect and reflect. Very good. All right, let's take a look at these two really cool facts. The first one is, if we have a composition of two reflections over two lines that intersect, it really is the equivalent of just one rotation about that point of intersection, and in fact the angle is actually 2 times the measure of the angle that's made between these two lines. And similarly, although different, if I have two parallel lines and I look at the composition of reflections across these two parallel lines, that's the same thing as just a translation. Armed with those observations, let's take a look at some interesting actual applications. Let's copy each figure and draw two lines of reflection that produce an equivalent transformation. So the first one, we have triangle ABC that's translated to triangle A prime, B prime, C prime. So it literally is a translation. Okay? And I want to now draw two lines where I can now do reflections and get there. Well, how do I do that? Well, the answer is that what I basically have to do is I've got to find the line that, first of all, I've got to find the point that's halfway between A and A prime. Now you can pick any points at all, corresponding points, B and B prime, C and C prime. And what you want to do is you want to actually find the midpoint between them, and then find the midpoint between those as well. So here's what we do. We take a straight edge. I'm going to do this in a color that hopefully will be somewhat invisible. And pick two corresponding vertices, so A and A prime, for example, and connect them. And now find the midpoint. And so you can find the midpoint by either using some geometry, or eyeballing it, or measuring it, whatever you like. I'll measure an eyeball. There's the midpoint. And then you take each segment left over and take half of that. So find the midpoint of each of these segments. And what you do now is we draw lines that are perpendicular to this line, but pass through this second midpoint and this second midpoint. So I will do that for you right now live. So there's one line. And these lines are going to be parallel since they're both perpendicular to the same line, the line that passes through A and A prime. We know they're going to be parallel. That's good. Because we know that a translation can be thought of as two reflections over two parallel lines. So I claim those are the parallel lines. And let's see if we can just for fun, I'll try to act it out for you right now live. I'm going to start here. I'm going to try to reflect over this line and then reflect over this line and see if we can get back to here. Okay, I'm doing this live. Don't get mad at me. It doesn't work. If I'm going to reflect around here, that means I just pivot everything right along here. Pivot everything right along here. So it sort of becomes like that. Doesn't that kind of look like the reflection? If you took this, doesn't that look like a mirror image of that? That looks good. And now if you take this and reflect it over this line, in fact, you can see this works out perfectly. Check it out. You see what that point is? That's touching at the midpoint of the whole thing. And we know that's halfway in between here and here. So that point will definitely get mapped to here. So you can see that this point A first gets mapped to the midpoint and then gets mapped to A prime. So it matches perfectly. And you can see that if you look at this and this, they're sort of mirror images of each other. Forget about this one now. Just focus on this and this. Mirror images. So if I do it, it works perfectly. Very cool. Very cool. Let's try another one together. Here we go. Here we go. Here's the big one. So this is rotation with center at P, and we're taking D, E, F, and we're sending it to D prime, E prime, F prime. And so let me act it out for you. So we take this point, and around this point P, we're going to rotate it. Bang, and there it is. And now I want to do this, I want to actually show this as reflections across two lines, and we know the lines are going to cross, they're going to cross at P. How can I find out exactly where to draw those lines? Well, what we do is the exact same procedure as before, the analogous procedure. We pick two corresponding points. I'm going to pick D and D prime, and connect those points to P. So make two rays, basically. And then what you want to do is you want to bisect that angle. And to actually bisect the angle correctly, maybe I'll do it really fast just for fun. You've got to do some arc stuff. Okay, so there I bisect the angle as best I can. And then what you do is you bisect again. So if you bisect again, which you would use a compass again. I'll do this here. And then here. These are the two lines that we use. So in fact, the lines, let me actually make sure they're really clear, are these lines here. These lines. And this line. The bisector of the bisector. Bisect the angle once, bisect the angle again. And so what that means is, if we start here, and we do a reflection around this line, we get something that looks like this. If we reflect it around this line, look what happens. It reflects to here. You can see it live. Absolutely cool. You can take a couple of transformations and turn them into just one.